Okay, so this is a continuation of our same exercise, which is exercise 6. And now we are on question number 4. So I want us to consider what we are given in this activity or in this exercise that we are given. So with this information that we have, we are given DF is a tangent from D to the point F. So this is a tangent. We are given as a tangent to the circle at E. And also you're given the angle KEF as 35 degrees, this angle K to E to F that is in between the tangent and the chord. So as you are reading this information, some of the theorems also, they are supposed to just flow out because you have them. Angle between a tangent and a chord is equal to the angle in the alternate segment. This chord EF, EK, it creates an angle. If we take a closer look, it creates an angle at H3, meaning to say with this concept, we can say that the angle here is going to be 35 degrees. This is what we can see from this information. We're just reading the information. We're not answering anything. Just from the information. All right. We are also given this is 31 degrees or HG from O to H to G. This angle is 31 degrees. Okay, we'll talk about that later on. EK is equal to HK. From E to K, it is the same as from H to the point K. That is the indication of these lines that we are seeing there. So we know that if these two are the same, all right, if these two are of equal length, these two sides, the angles that are opposite these sides must be equal also. So which are the angles? E4 and H3. So these two angles are supposed to be equal. So if they are equal, it means this also is supposed to be 35 degrees, meaning to say our E4 also is supposed to be 35 degrees. That is what we can see from there. All right. So the question was, let us answer our question. Determine this E4. So already we calculated this. So E4, as I said, it is equal to angle H3, which is equal to 35 degrees. So that one, we took it, the H3, we took it from the tan chord. Remember, angle H3, which is equal to 35 degrees. This one, we took it from the angle between a tan and a chord. So just going to write in short, tan chord. Angle between a tangent and chord is equal to the angle in the alternate segment. All right, what about angle K? So the second part, which is 4.2, was to determine angle K. So let us see where our angle K is. Angle K is on this part. All right, so this is our angle K. So as we can see, to determine angle K, we can use angles in a triangle. We know that angles in a triangle, they add up to 180 degrees. So meaning to say angle K from 180 degrees, we are going to subtract these two angles. Remember, we've got this angle and this angle as 35 and 35 degrees. So we add these two angles, subtract them from 180 degrees. So that's 180 minus 70 degrees, which is going to give us 110 degrees. All right, so this is our angle K, which is 110 degrees. Just going to indicate on our diagram. We might need this. You never know. All right, DEH. So we need angle DEH. All right, so let us see where are we having this. That is our 4.3 angle DEH. All right. So if we consider on our diagram, this is D, this is E, and this is H. We are talking about the whole of this angle here, the whole of this angle, the combination from D to E to H. So I want you to properly consider this. Okay. I want you to properly consider this. Remember, DF is a tangent. So DEF, the DEH, this angle that is indicated here, the one that we want to calculate, it is an angle that is between the tangent and the chord, which is the chord EH. We are talking about the chord EH, angle between a tangent and a chord. must be equal to the angle in the alternate segment. So what you do is that you hold this chord EH. Hold this chord, it creates angle where at the circumference, at this side, in the alternate, in the other segment, not this segment. You consider the alternate segment, this side. So this chord, it creates angle at K. So this angle at K is the same as the angle at D. The whole of this angle at D is going to be 100. The whole of this angle at E, which is DEH, is going to be also 110 degrees. So this is simply from the angle between a tangent and a chord equal to the angle in the what? Alternate segment. So the tangent DF and the chord EH. Okay, so you can write that in full. I'm just going to give you just a short part to consider that. So that was our 4.3. Let us consider 4.4, which is to determine the angle G. All right, angle G is at this point here. This is our angle G. So if you consider from E to K to H to G, these 4 points are on the circumference of a circle. These points, all of these 4 points. So, this is a cyclic quadrilateral. And what is it about a cyclic quadrilateral? Opposite angles of a cyclic quadrilateral are supplementary. Opposite angles of a cyclic quad are supplementary. So this is simply going to be 180 minus 110 degrees, which is equal to 70 degrees. So this, we took it from the opposite angles of a what? Of a cyclic quadrilateral. The opposite angles of a cyclic quadrilateral, they are supplementary. They add up to 180 degrees. All right, let us move on to 4.5, which is to determine angle O1. So O1 is at this point. This is where we are having our O1 already indicated. All right. So remember, we have determined angle G, which is 70 degrees. This is 70 degrees. From the chord EH, this chord EH, if you hold this chord, you will see that it is creating, or it is subtending, an angle at G like this, which is the angle at the circumference. The same chord, if we go back to this same chord, we hold it back, you see that it creates an angle again at the center, which is at O1. So what's the concept? We know that this angle that is at the center must be twice the angle at the circumference. So meaning, if this is the case, our 4.5, meaning to say our angle O1 is going to be 70 degrees times 2. That is going to be twice, and that is 140 degrees. So this is about angle at the center. So we're talking about angle at the center. Remember, angle at the center is twice angle at the circumference. So meaning this is going to be 140 degrees. So there we have got 140 degrees. Okay. Let's move on to the other part, which is to determine OED from O to E to D. All right, that's 4.6. So 4.6, we're going to determine from O to E to D. All right. So this is the idea there. Let us see, where are we having this on our diagram? That is from point O to E to D. So if you consider this is O to E to D like this. This is the angle that we want. So what is the idea there? This is a radius, and this is a tangent. A radius and a tangent, they meet at 90 degrees. Remember, they are perpendicular. So that means this is simply 90 degrees. We are simply talking about what? A tangent and a radius. A tangent and a radius, they are perpendicular. They meet at 90 degrees. All right. That is what we had there. 4.6. Which is to determine 4.7, which is to determine angle E1. So remember, okay, let us indicate our E1. This is part of E1, this one. So it is from this point up to this point. This is our E1. So if you were to consider this, you were going to see that All right, that is angle E1. This angle E1, if you were to consider this properly here, you will see that this angle that we are seeing, it is between a tangent and a chord. But this time we are considering chord EG, this chord EG. Remember, we considered EH before, but this time we're considering EG, E to G. So if we consider the chord EG, this one, this chord EG, it subtends an angle somewhere. It must subtend at the circumference because we need the concept that the angle between a chord, between the tangent and the chord must be equal to the angle in the alternate. If you hold this to the circumference at H, you hold also G, go with it to the circumference. There's an angle created at the circumference there, which is in the alternate segment from E to H back to G from the chord EG. What is the angle that we are talking about? This is the wall of this angle here, the wall of this angle, which is EG to H. So meaning to say, this angle E1 is equal to the angle EH to G. Angle EH to G. There we are simply talking about the same part of our angle between a tangent and a chord. So I'm just going to write in short tan chord. The tangent that we're talking about is DF. The chord is EG. We are referring to the chord EG. So if that is the case, then let us just find this angle EG, E to H to G. How can we determine this? From E to H to G. Already this is 31 degrees, which is part of H. So we are going to need this H2. So let's just say this is our H1. So we're going to need H2. How are you going to determine H2? Remember, from O to H, that's a radius. From O to E, that's a radius again. So what is it that we know? These two, they are equal. So it follows that the angles that are opposite these sides, they are supposed to be equal. So if that is the case, we are going to see that angle A3 must be equal to angle H2. All right. So in this case, we're going to see that angle A3 is equal to angle H2. All right. These are angles opposite equal sides. Angles opposite equal sides. So since angles in a triangle, they add up to 180 and already there's a 140 there. So we are going to simply subtract this 140 from 180 degrees. We subtract this, but because these two angles are equal, the difference that we have is for these two angles that we are seeing. Angle E3 and angle, the difference that we are seeing. So how do you determine one of these? Because we are saying they are equal. So how are you going to determine one of these? You divide by 2. So it means our angle E3, which is equal to angle H2, is going to be given 180 minus 140. That's 20 divided by 2. That's 180 minus that's 40 there. Then 40 divided by 2, that will be 20 degrees. Or just use your calculator at once. So if E3 is 20 degrees, this one, if this is 20 degrees, like I'm saying, this is also 20 degrees. So remember, we want to calculate angle E1. So therefore, our angle E1, which we said it is equal to angle EHG, which is from E to H to G. So angle EHG is a combination now of these two angles. The angle of 20 degrees here and these 31 degrees. So we are going to add these two angles, 20 plus 31 degrees. And this is going to give us 51 degrees at the end. So meaning to say angle E1 here, that is where we are having our angle E1, the whole of this angle here. the whole of this angle that we are seeing is 51 degrees. This is our E1. Remember, the 100 was that one that was covering everything. Remember the one that we calculated before this 110. It was for the angle DEH. So don't confuse with this one. Don't confuse these values. All right. So this was our angle E1. Let's consider another part. 4.8. What type of quadrilateral is EOHK? Justify your answer. All right. We have a quadrilateral, as we can see from our diagram. It's a quadrilateral, but we need to know this type of quadrilateral. What is it? Is it a parallelogram? Is it a kite? Is it a rhombus? What is it that we have? So they are saying this is 4.8. So the quadrilateral is given as E or HK. This is our quadrilateral from E to O to H to K. Then we go back to E like that. This is the quadrilateral that you're talking about. If you are to see this, you are going to, if you are to consider this properly, OE is the radius, which we said it is the same as OH. OE is equal to OH. We are talking about the radius concept given that. Also, you are going to see that E to K, we are given from E to K and from K to H. These two, they are equal. These two sides here, the sides that are like this on a shape where they meet at a certain point, they are called adjacent sides. So these are adjacent sides, So what is it that we know about our quadrilaterals when it comes to a condition where the adjacent sides are equal? Which special quadrilateral has these properties of the pairs of adjacent sides equal? Because these pairs, they're equal. This pair and this pair, they're equal. What type of quadrilateral is that? This is a kite. So E or HK is a kite. So the reason that majorly that we are seeing the major reason there, it is because of these two pairs of adjacent sides equal. That is two pairs of adjacent sides equal. So each and every part that you are going, there is a specific reason for a quadrilateral. These quadrilaterals, they share something, but each quadrilateral has got its own. It has got its own. If you talk of a trapezium, there's got one pair of opposite sides parallel, which you do not find in any other quadrilateral. So each and every, there is a special point on each. This is from our grade 10. Remember your grade 10, we talked about these quadrilaterals. All right. So that was our condition. So we saw that from the adjacent sides. Also, if you consider if this is a kite, you're going to see that the angle, this one, the angle H, which is H2 and H3 combined, must be equal to this E4 and E3 combined. As you can see, this is exactly 35 plus 20. 35 plus 20. These are the properties of a kite. Only that this kite is just slanted, not the way that, but that's a kite. The adjacent, the major part is on the adjacent side. And we know that if it is like that, because we have proved that is a kite. So it means from O to K, if you draw a line from O going to K like this line is the diagonal, just like this diagonal that we are seeing. But the diagonal, what it does, it affects this part of our adjacent sides. This one. So it bisects these angles on the adjacent sides. So it bisects this angle and this, this angle to be two equal angles. That is, if it is 140 divided by 2, it's going to be 70. It also bisects these two angles. No, not the other way. Only these ones on the adjacent, not here, not these ones. No, these two, these one, they are equal. Those one, they are equal. So this is this bisector EQ, this one, this bisector EQ. It is not just a bisector. I mean, this line, okay, it is not just a bisector. It bisects even the EH into two equal parts. These are the properties of a kite. So EH is also divided into two equal parts. So this line, OK, does a special part. Divides the angles into two equal parts. So as we are used when we see this kite, when it is like this. So already we've proved, I'm just going to remove this. We have already proved. So the problem is that when these shapes, they just turn around, we tend to have a confusion. It is because we are used to a kite when it is drawn in this way. When you see a diagram like this, you can see, okay, this is a kite. These two sides are the same. But this is the same thing that we are talking about. These two sides, adjacent sides, these two sides, adjacent sides. So this is what we have here. So this line that you draw from this point to here, let's say this is A, B, C, D, like this. AC, this one. The one from the adjacent sides, it is the one that bisects these two angles. So meaning to say, this angle, if this is 1, this is 2. If this is 1, if this is 2, it means A1 must be equal to angle A2. The same thing here, angle C1 must be equal to angle C2. But on this other part, it does not bisect. No, take note, B and D, they are not bisected. No, it is BD, the line BD, this one, the diagonal BD, which is bisected. So if this point is E, it means from B to E, it is going to be equal from E to D or D to E. What about the angle B and angle D? These two must be the same. Angle B must be equal to angle D. This is the idea. This angle H2 and H3 must be equal to E4 combined with what? With E3. They are not, these ones, they are not bisected. It's these ones on the adjacent sides. The ones that are from the adjacent sides, these ones, those are the ones that will be bisected. Not these other ones. No. These ones are, because this side and this side are not equal, remember. So that one does not apply on D and B. It's only that B and D will be equal. But when it comes to C, C will be bisected into two equal parts. So this is what I was explaining, this one. So meaning to say at O, this 140 is going to be divided into 2 so that this will be 70, the same at K, 110 divided by 2. That is the idea of the diagonal OK. All right. So these are some of the things that you just need to consider as you're answering your. It's not like we are there, but you are just giving your question to say, okay, I'm working with a cyclic, I'm working with a cyclic quadrilateral, I'm working with a triangle, I'm working with this. What are the properties of that shape? By knowing those properties, you also answer other questions. You will see that. All right. Let us see this other part. Prove that. As you can see this question, they are saying prove that OK perpendicularly bisects EH. So they are saying OK, this one from O to K, it is a perpendicular bisector of what? Of EH. Prove that. So how are we going to prove? Already we have proved that this is a what? A kite. So if it is a kite, this is what you see now what I was explaining before. So read some of these things, we have explained that. All right, so 4.9, we want to prove that OK is a perpendicular. All right, it's perpendicular bisects. So it is supposed to be a perpendicular bisector of what? Perpendicular bisector of EH. So is that so? That is the question. On a kite, it follows that these two, like I said, OK is a perpendicular because we have proved that before. So already remember, EOHK is a kite. This one is a kite. So this one is already proven. So if it is a kite, therefore it follows that OK diagonal OK bisects So this is what happens with the diagonal. It bisects what? EH. So meaning to say the bisector concept is there. Not just to bisect this EH, it also bisects this at 90 degrees. So you can also prove that with calculations if you want. Remember, I said this angle here is 110. So it is bisected into 2. So meaning to say 110 divided by 2 is going to be something like 55 degrees. So this will be 55 degrees. So if you subtract these angles, you're going to see that this is 90 degrees from 90, 180 degrees, 180 degrees minus these two angles, 55 and what? And 35. So 35 and 55 degrees. If you subtract these two angles from 180, you're going to obtain 90. Meaning to say this angle is 90, this angle is 90. So that is the angle that we are having at this point of intersection is 90 degrees. So it does not just bisect. Okay, this diagonal bisects EH at what? At 90 degrees. So therefore, that is the consideration there. So we are simply taking from the properties of a kite, and we can also consider these calculations as we have proved, because it's a kite. So you can take the properties of a kite. That is, when you proved something, you now take it as a concept, because you have already proved it before. So you take it from what you have proved to answer another part, if it is possible like that. So that is exactly what we have. So therefore, okay, perpendicularly, that is perpendicular, like this is bisects. So this one, it bisects EH. So the bisection is there to divide into two equal parts from the properties of a kite. The 90 degrees or everything is actually from the properties of a kite. All right. So this is what we're going to have on 4.10 is if KO is produced, will it pass through G? It's a question. Justify your answer. If this KO that we are seeing here, if it is produced, like if you draw it, you extend it, is it going to pass through G? That is the question. So you don't draw it like this, then you say, no, it does not pass. You have to prove that. Okay, so how can we prove that truly it passes or not? Because the question is, we want to know it passes through this or not. That is the question. You're supposed to answer there, is it yes or no? So if we are to consider this on KO, that is it, like this. If you are to consider this on K to O, let's say truly that it passes this. Let's say this one was going to pass. Let's just force it to be like this. If it was going to pass through this G, remember what I said. It is going to be like this. KH here, which is this chord, subtends the angle at the center, which is now 70 degrees. Remember, it was 140. Now it divided, so it's going to be 70. It also must subtend an angle at the circumference at G, which is half of the 70. So if that is 70, divide by 2, that will be 35 degrees. So meaning to say, if this is to pass, I'm saying if, I'm not saying it passes. If this is to pass through this point, it must give us these considerations that I'm explaining to say that the angle at the center must be twice the angle at the circumference. So is that the case? We want to see that. All right. So if you consider K to O to H, angle K to O to H, this angle here, K to O to H, that is the one that I said it is being divided into two equal parts from 140 degrees. So it's 140 divided by 2, which is 70 degrees. So meaning to say this piece here, this part here, it is 70 degrees. Okay? If you calculate from K to G to H, what is going to be this angle? from K to G to H, we must have half of this 70, which is 35. So that is what we want to prove. So you don't have this, no, you have to calculate it from somewhere. We have to use other values, other calculation to prove that. So how can we calculate this KGH? Because this one we're given as a combined angle is 70, so you can't divide that by 2. No, there's nothing like that. We have to consider from our calculations. All right. So if you consider this is a triangle. Inside a triangle, angles inside a triangle, they add up to 180 degrees. So inside this triangle K to G to H like this, we are going to subtract all these angles inside of this triangle. Which angles are we talking about? There's a 55 degrees there. All right. There is H3, which is 35 degrees. There is H2, which is 20 degrees. There is also a 31 degrees, or which we can consider as H1. That is all these angles. All these angles, they are inside of the triangle. They are forming the major angles of a triangle. These angles that we are seeing there, they are forming the major angles of a triangle. So those are the ones that you consider. You don't consider an angle such as this one that are you consider the angles on the outer part of the triangle. So if you are to subtract everything on this part, you are going to obtain 39 degrees. That is what we are having there. We are obtaining 39 degrees after subtracting all these angles, which is not what you're supposed to have, because if you are to divide this by 2, the angle at the center is twice angle at the circumference. We are supposed to have half of 70, which is 35, not 39, not another angle. So meaning to say, this is not exactly what we want. This is not exactly what we want. It is not fulfilling exactly what we want. So this one is a straight no. So that's a no on this one. Why? We were supposed to see the angle at the center being twice, but it's not like that. So we are saying the angle at the center, not is not. So this one is not twice or is not double. All right, is not twice or double the angle at the circumference. The angle at the circumference. So if it was going to double, it means truly this line passes through the circumference of the circle at what? At G. But this line from K to O, it means it passes through the circumference of the circle, but not at what? But not at G. Maybe somewhere there, but not at G. If it was to pass at G, it was supposed to maintain this property that we are talking about of the angle at the center concept. The angle at the center being twice the angle at the what? At the circumference. But we can see that it's the other way around. So it's not going to pass through. All right, so that is how we're supposed to have justify this one. So these are your typical questions that you are going to have. We need a lot of these questions in our revisions. Make sure that you do revise as much as you can as you are preparing for your exams. So just make sure you work with more questions. Practice as much as you can.